mechanics is a particular case of relativity. It still applies. So this means that Newtonian model hypothesis, the explanation was a very good one. But we know a little bit more nowadays, and we can explain Newtonian plus other things. The same applies to your systems. Now let's go to errors. Errors happen. Who will say that? Errors always happen. And what is the source of error? There are a lot of sources of errors. The first classification can be the human errors and instrumental errors. We can be even much more splitting hairs and say we can talk even about methodological errors, the way in which you are doing your test. Sometimes you take a measurement and then you take another one. If you reverse the order, you may get different results. That will be a methodological error. But they happen. They happen, even with the same person. If you take manual, anybody that has took manual measurements will know that your results change. And change in the time of the day, change with your mood, change if it is the morning or after lunch, after you are drowsy, especially if you have drunk a little bit of wine or beer. This happens. And actually, one has to take into account that even scientists, they take human errors very seriously. If you are an astronomer, nowadays it's all automated, but as recently as 15 years ago, astronomers were behind the telescope or measure the position of the stars and other objects through pictures. And it was manual measurements that they were doing. The measurements that they were getting, they assigned it an error due to the instrument, the telescope. If it was located in Chile, in Antarctica, or besides Vancouver. And in addition, another factor that they included were their human errors. And it was a very complicated formula in which they were able to calculate their own error, human error. And it depends on the years of experience, the age, and I don't know how many other factors. Let's see this beautiful graph. I don't know, it's not very clear, but this is 11.0 and that is 14.5. It's not 145. Well, let's account for errors. If my errors bars is plus minus 1, what I see here, I see this is time, this is 1 to the time. What will say? Well, this means that whatever is the phenomena that is happening here increases with the time. This is an extremely valid conclusion. You can see. However, if my error bars are plus minus 3, then I cannot say that. My error bars will be plus minus 3, and this point will be larger than here. This will be simply noise. Nothing else than noise. There is no phenomena here. You don't have enough data to deny or to affirm, to state anything here. A lot of people have the tendency to say, oh no, but this is still interesting. No, you can say that. Don't waste your time. Put your energy into analyzing other phenomena, or if you want, to refine your test. Perhaps you can go and reduce these error bars, and then you can repeat your test, and then perhaps you can see a trend. But if the error bars are plus minus 3, forget about it, it's noise. Data, the meaning of data, how the data that we get in performance is influenced. It's influenced by the hardware. It's influenced if you are using a NAS, a SATA, or whatever kind of hard drive. It's influenced by your bandwidth and your network. It's influenced by the position of the different machines in the architecture of the network. In addition, of course, of the architecture of the software and how well it has been coded, etc., etc. The configuration, we have found in the time a lot of configuration errors simply based, a lot of performance problems based on configuration errors, simply that Oracle was not correctly optimized or correctly installed or correctly configured. So you need to take into account all these factors in order to explain later the data that you are obtaining. More meaning of data. We have to be very careful in the requirements. focus on the business analyst. The requirements need to be precise. Results, pass, fail, the performance is acceptable or is unacceptable, are as good as the requirements are good. Usually, I can put this example. Event A should not take more than X seconds. Okay, this is a very clear requirement. Life is beautiful. Let's go ahead. These are my results, by the way. The event time and 10. What exactly means the previous requirement? Means this? This is what strictly it means. However, most of the time, when people is writing that sort of requirements, is thinking on that. So this is the first thing that we need to have into account. Performance numbers have a distribution. And this distribution can be very, very wild, can be very huge, depending on all the different factors. And again, think that there is going to be a little bit of variation due to the access time in the hard drive. And then the network is going to put a little bit more variation added to the previous one. Actually, it's not added, technically it will be convoluted to the previous one. And all the following little variations are going to convolute to each other, and you are going to have a distribution, and sometimes the standard distribution can be quite large. So the first thing is that how we are going to write the requirement. The requirement in this case is whoever wrote the requirement said that we'll have to say a different requirement, saying implying the average of event A should not take more than X seconds. This can be written in other different ways. It can be percentiles. The event A should not take more than X seconds 50% of the time. Realize that if we say that event A should never ever take more than 8 seconds, this is a perfectly valid requirement, but maybe very, very difficult to achieve. Only keep that in mind. So, when we have a lot of data, we need to apply statistics. So we need some statistical concepts. I will try to be light on that and go fast. So the next slides are going to go a little bit fast. However, I would like to introduce two very important statistical concepts. That is, a statistically significant and a statistically equivalent. A statistically significant means that the measurement is good enough to do your statistics. So all that measurements that you took after dinner and after 2 beers, perhaps are not statistically significant. But this means that you have to throw them away. This is what it means. No, this is a possibility, and this has happened to me, not with beer, with wine. But this has happened to me. Can happen also that you don't realize and someone has been messing up with your environment. If someone has been messing up with your environment, I am sorry, your results will not be statistically significant, thrown away. The other thing is that it needs to be statistically equivalent. This means that are obtained in the same conditions. The second example that someone has been messing up with your environment, they will be statistically significant, but for another kind of test, not for the test that you were doing. So this is the things that you have to keep in mind, two very important concepts. These are some rules in order to check if your data is statistically equivalent. This is mainly if you are getting data and the data doesn't make a lot of sense, what's happened with it. I'm going to discard this data, I'm going to accept this data. These are some rules of thumb. The next slide explains it a little bit better. The rule of thumb in this case is that we can see that test number 3 is not statistically equivalent to the other test. And the definition that I had put before is when the 90 percentile, this means that when 90% of the results are under this number, this can be the maximum, this can be the minimum, but this number covers 90% of the result that you have got. It's larger than the maximum or minimum of the other test that you have done, then it's not statistically significant.